So next we are going to start the intermediate value theorem. We have already seen that if we have a continuous function like this, say to make the function more concrete, we take this closed interval. It is the domain of the function. Then the function attains its maximum value somewhere in the domain and the minimum value somewhere in the domain. Okay, they always exist. We have already seen this. And now in this section we are going to see that it also attains all the values in between the maximum and the minimum. So that is why the intermediate value theorem. The function will attain all the intermediate values lying in between its maximum value and minimum value. So let's see the statement of the theorem. The statement is basically just this. We have, again, just like how we started another theorem in the previous section, namely the maximum principle, we have two real numbers a and b such that a is less than b, and there is a continuous real valued function f with this closed interval as its domain. Then for any real number y which lies between f of a and f of b. Now that can happen in one of these two ways. Such that this or this. For any such y, there exists a point C in the domain of f for which y is equal to the f image of C. So what this theorem states is that if we have such a continuous function, then it assumes or attains all the real numbers lying between fa and fb. This is not exactly what we said just now, that f assumes all the real numbers that lie between the minimum value and the maximum value, because fa and fb may not be the minimum or maximum, but this is what we have in this theorem, and a corollary to this theorem will be that which involves maximum and minimum. So now we are going to see the proof of this theorem. Now in the proof, of course, we will not show both these cases because they are similar. The author has only shown this one. So let's see that. We only consider this case. Now we can immediately dispose of two trivial situations. If y is actually equal to f of a or y is equal to f of b, then we are done, because we want to show that y is the f image of some point, some c. In this case you can take that c to be a, and in this case you can take that c to be b. So assume that neither is true, that is y is strictly greater than a and greater than f of a and strictly less than f of b. Now next we are going to consider this set E. It is the set of all real numbers x lying in our domain such that f of x is strictly less than that y, our y. We are next going to see two things about this set E. The first thing is that E is non-empty. There is at least one element in E, which you have probably already guessed. You see, from this inequality, we see that A is an element in A comma B whose F image is less than Y. So that means A is in E. So E is non-empty since A is in E. There will be likely other elements also, but at least A is there. Also, since E is a subset of this closed interval, because by definition E is a subset, E is bounded above or bounded from above with B and upper bound. Because E is a subset of A comma B, so any element of E would belong to this interval and as such would have to be less than or equal to B. So that's why B is an upper bound for E. So E is non-empty and bounded from above. So by the least upper bound property, the supremum of E exists. Of course it always exists, but in this case, because of these things, it's a real number. Okay. Now what can we say about this C? You see, because A is in E and C being the supremum of E is also an upper bound for E, so A would be less than or equal to C. Obviously, because every element of E has to be less than or equal to every upper bound. So in particular, A is less than or equal to C. Besides this, B is an upper bound for E, but C is the least upper bound. So C is also less than or equal to B. That is, this C itself is in A comma B. Alright. Now the next thing we are going to do is that we are now going to claim this. Our claim is that previous value y is actually equal to f of c. So this is the c that we were seeking, or we were mentioning in this statement. Now how to prove this? We will prove this by actually proving both these inequalities. And f of c less than or equal to y. That is our strategy. So let's see how that can be done. The first thing we are going to do is we are going to use the fact that c is the supremum. It is the least upper bound of e. We are now going to use the least nature of this number. Consider any positive integer n. N will vary, but let n be any positive integer. And you consider this number c minus 1 over n. Obviously this number is less than c. It is less than c. Because c is the least upper bound, so this number being less than even that can no longer be an upper bound for e, which means that at least one element of e has to exceed this, has to be strictly greater than this one, making it not an upper bound. So let xn be such an element. Note that xn has to come from e. Let us also write that as well. But because xn is after all coming from e and c is an upper bound for e, it's the least upper bound, but it's an upper bound after all. So xn at the same time has to be less than or equal to c. So what this statement says is that for any positive integer n, this set is non-empty. This set is non-empty, no matter what the value of n is. So as you consider all such sets, all of them are non-empty. So you now have a collection of infinitely many non-empty sets. So the axiom of choice allows you to choose one element from each set. And that's how you get a sequence whose terms satisfy these conditions. Note that because each term xn is coming from e, this sequence is a sequence in e. Moreover, we can see from these inequalities that this, of course, if you look at these terms and these terms I am saying, but all of them are equal to c. As n changes, c of course stays c. So we are now looking at three sequences linked by these inequalities. One of them is this, the other one is this, and the other one is this constant sequence, all of whose terms are equal to c. Now the limit of this leftmost sequence is of course c, because 1 over n approaches 0 as n approaches infinity, and the constant sequence c of course also has limit c. So by the squeeze test, the sequence in between is also convergent and it converges to C. Alright. But because Xn is a sequence in E and E is a subset of our closed interval a comma b, Xn is after all a sequence in a comma b, which is the domain of our f. Now you use the fact that f is continuous at C. Note that it makes sense also to say this, that f is continuous at C, because C is a point in the domain of f. If we did not know whether C belongs to this or not, this will not make sense. Okay. So now f is continuous at C and Xn is a sequence in the domain of f which is converging to C. So by the sequential formulation of continuity, we have this. Limit of f of Xn will be equal to f of C. Okay. But now you come to the, let us go back to the definition of E. What was E? Let's just recall that. E was the set of all x in a comma b such that f of x is less than y. This is what E is. Since each xn is in E, we have these inequalities. For all positive integers n. And so, by the comparison principle, if you take limit on both sides, the right hand side of course is constant with respect to n. It does not change as n changes. The left hand side, however, has the limit f of c. So by the comparison principle, after taking limit, we get this: f of c is less than or equal to y. Keep in mind that the comparison principle only gives us ordinary inequality, not strict inequality. Okay, such things have already been discussed about before, where you have two sequences where the nth terms maintain a strict inequality, but the limits are not in that inequality. Okay, but anyway, the point here is that we will get something like this, which if you see is one of the things that we were seeking. F of c is less than y. Now we need to prove this opposite inequality. And for that, what we are going to do is this. Now recall that our y lies strictly between fa and fb. That is the case we are in right now, right? We are in this case. and we now have this as well. F of c is less than or equal to y. So of course c cannot be equal to b, because otherwise f of c would be greater than y and as well as less than or equal to y, contradicting the trichotomy of order relation. So that is why c is not equal to p. However, we already know that c lies in this interval, so that means c is less than or equal to p. Combine that with this and we get this fact: c is strictly less than p, which means what? It implies b minus c is a positive real number. Now b minus c may be close to 0, may be far away from 0, we don't know. But what we do know is this: by the Archimedean principle, there exists a positive integer which is large enough such that we did not give any name to it, a positive integer capital N, say, such that the reciprocal of n is small, it's smaller than b minus c. In spite of being positive itself, it's still smaller than b minus c. We can choose a large enough n like that, and it follows from the Archimedean principle. We already know these things. Hence, 1 over n, we are writing 1 over n first, okay, so the inequality will change direction, is less than 1 over small n is less than b minus c for all n greater than n. If we consider even larger integers n, then their reciprocals will be even more small. Okay, so all of them will be less than b minus c. That is, c plus 1 over n is less than b for all n greater than n, right? Now, we are of course again looking at a sequence whose nth term is c plus 1 over n. This inequality tells us what? It tells us that c plus 1 over n, this sequence, is a sequence in our original domain of f, a comma b. But exactly why? We can already see from these inequalities that all the terms of this sequence are less than b. But also, all the terms are strictly greater than c as well, and c itself being in this interval is greater than or equal to a. So that is why all these terms lie between a and b, and as such this is a sequence in a comma b. Also, of course, this sequence I should have written limit. But anyway, we can write in words also. This converges to C clearly. Now, since C is an upper bound of E and C is less than C plus 1 over N for what we are talking about is a sequence which starts with well, if you want, you can, the author has taken n to be strictly greater than n. We can take n greater than or equal to n also. It won't matter, but then we can write n here. The sequence that we actually have starts from n, not necessarily 1. Ultimately, it's not going to matter where it starts, but we cannot write 1. Okay. For all n greater than or equal to n. Writing a possibility for equality here itself is it's not a mistake, okay, because the inequality that we have here is in fact true for capital N as well. Okay, so we can take small n to be capital N. So now what do we see? Because C is an upper bound for E and each term of our sequence is greater than C, so none of them of course can belong to E. That's because any element of E has to be less than or equal to C. These are, however, all of them greater than C. Thus, is not in E for all n greater than or equal to n. However, what are the elements that are in E? They are real numbers in this interval whose f images are strictly less than y by the definition of E. So this implies the f images of these numbers which are not in E then must not be less than y, must all be greater than or equal to y, because these are not in E. That is, f of C plus 1 over n must be greater than or equal to y. Let's also write the variation for all n greater than or equal to n. Now again you use the fact that f is continuous at C and this is a sequence in our domain of f which converges to C. Hence, since f is continuous at C, the limit of f of C plus 1 over n as n approaches infinity is f of C. And then you use the comparison principle along with this limit on these inequalities, and that will give you next this. So by the comparison principle, the limit of this is greater than or equal to pi, that is f of c is greater than or equal to pi. So you can see that we have also got the other inequality that we were seeking. Hence, f of c is equal to y. That was the claim. So this completes the proof of the intermediate value theorem. So what the theorem says basically is just this. You have let's recall, okay. Let's summarize the theorem briefly. We have a continuous function like this, whose domain is a closed interval, and there is a real number y, which may be any real number, between fa and fb, either like this or like this, as the case may be. Then y is also an f image for some c in a comma b. Now the hypothesis that f is continuous is important, because without continuity this may not be true, and one such example is given in the text. A very simple example. If consider this function, defined by this following rule or formula, the function is constantly -1 if your input is non-positive. It's either less than 0 or equal to 0, and it's constantly 1 if your input is positive. Now it's the kind of function that we are considering here, except for the fact that it's not continuous. It is not continuous at 0, which you can clearly see. Now what is f of -1? Because -1 is negative, so it's -1. And what is f of 1? It's of course 1. Now you think you take any value between these two f values. The author has taken 0. So this is our y now. But you can clearly see that there is no x or there is no c in this closed interval for which f of c is equal to 0. Because the there are only two f values, -1 and 1. F never attains 0. So failure of this conclusion in this case is due to the fact that f fails to be continuous. So it has jumped past the value 0. When the x approaches 0 from the left side, the function is constantly -1. Even at 0 also it's -1, but then suddenly it jumps to the value 1. Due to that discontinuity, it misses the value 0, or in fact any other value in between. Continuous functions cannot do that. They have to go through all those intermediate values. Okay. So this is why we need continuity. Now, just like the maximum and minimum values of such a function can be attained at multiple points, intermediate values also can be attained at multiple points, not necessarily always only at one point. So the next remark is about that. So for this remark, we considered this function. From minus 2 comma 2 into R, and the rule for the function is this x cube minus x. It's a polynomial function, so we know that it's continuous. Okay. So by our intermediate value theorem, any value lying in between f of minus 2 and f of 2 will be attained by f at some point. So let's see what the f values are at the boundary points. F of minus 2 is minus 8 plus 2, that means minus 6. Whereas f of 2 is 8 minus 2, that is 6. So we can again consider 0. 0 lies between minus 6 and 6, so 0 is our y. Now one can see that 0 of course will be assumed by f somewhere, but actually it is assumed at 3 points. F of minus 1, f of 0 and f of 1, all of them are equal to 0. You can verify it here, and all of these points lie inside the domain. Okay, so at multiple points, yes, any intermediate value may be assumed. There is another remark after this. You see, we have already established theoretically existence of nth root of any positive real number, where n is any positive integer. But we can also use the intermediate value theorem for that. I mean, we did it long ago, but still using the intermediate value theorem also it can be done. For example, say someone wants to prove that there exists a positive square root of 2, namely a positive real number whose square is equal to 2, using the intermediate value theorem. So how that can be done is, you have to consider this function f from 0 comma 2 into R, and the rule is just squaring the input. So it's our familiar square function restricted to this interval. We already know that the entire square function is continuous, so its restriction on this interval is also continuous. Okay. Now what are the values at the boundary points? F of 0 is 0 and f of 2 is 2 square, which is 4. Now the y value that we can choose in this case can be taken to be 2, because 2 lies between 0 and 4. So by the intermediate value theorem, there exists a number c in the domain of the function 0 comma 2 such that two is the f image of C, that is C square. And because C actually cannot be 0, so C has to be positive. So that of course comes out immediately, and that C is clearly C is greater than 0. That C is a positive square root of 2. I say a positive square root because just using the theorem like this tells us that such a C exists, but it does not necessarily tell us that the C is unique. That can be proved separately, but at least one positive square root of 2 exists. It can be shown like this. And once you show that it is unique, you can then denote it by some symbol, and the usual symbol of course is this. Okay. And finally, we come to the corollary, which is again about intermediate values, but now maximum and minimum values will be involved. So it will be item 974. The start of the corollary is just like how we started the maximum principle and the intermediate value theorem today. That is, A and B are two real numbers such that A is less than B, and if from A comma B to R be a continuous function. Now we already know from the maximum principle that the minimum value and the maximum value of f are attained within this interval itself. So let us name these quantities. Let small m be the infimum of the f values inside our interval, and capital M be the supremum of all the f values inside our interval. Then for any real number y in between this small m and capital M, there will be a point in the domain whose f image is equal to y. This time of course we do not have another set of inequalities because this is the smaller one and this is the larger one. For which y is equal to f of c. Moreover, this corollary actually has a name also. It's named images of continuous functions. I think that's what it's named. Let me see. Yeah, images of continuous functions. Moreover, it also says this, that the image of the entire domain under F is actually equal to this closed interval. whose boundary points are respectively this infimum and supremum. The proof of this corollary is one of the exercises, so we will see it there itself, and that in fact completes the theory part of this section, and it completes today's video also. Now I thought of doing field theory this coming Tuesday, but two of my viewers want calculus, so let's see calculus on Tuesday. So that's just it. Signing off for tonight. See you on Tuesday. Until then, this is me, Lucifer from a mathematical room. Have a nice night.